As a continuation from the last module, so we now look into the resistance network aspect of it. What it is that now as I discussed last module, the heat that flows from the die down from this point, the red dot down, is usually neglected or can be considered as negligible, and the heat that flows on the top can be split into two major parts. One is this red to this orangish dot, that is called the junction to case resistance. The heat spreader is often referred as case for industrial context. So, this resistance is often specified by the manufacturer of the device. So, this RJC is typically not specified, or the case temperature is only specified. This is called the case temperature or the heat spreader temperature that are. So, the heat sink design then becomes the challenge of from this case design or case to air or the ambient temperature. In this case air, if it is liquid, one takes into account the liquid inlet temperature. So, the heat flows from the case into the air, and here again there is a thermal interface material and a heat sink that is involved in this. So, this thermal interface, so this is the typical resistance network that one encounters. If one is interested in transient, then one has to account either a caver or faster network. This is just one example. We will not look into the transient networks, thermal networks, but it becomes important when dealing with power electronics, these RC networks. So, nevertheless, what we are going to focus is from this point the heat spreader and the ambient. And moving forward is that now what is the spreading resistance? We will just look at one example of how heat source size affects the temperature. This is an example where you have this greenish part is your heat source, and this green is the substrate over which the heat source is mounted, and heat or flow air flow happens very slowly, about 2 meters per second across this, and we observe what is the temperature rise, and you can see that roughly about 92 degrees Celsius is what is seen as the air contacts. So, it is much cooler at the entrance, where at this point the air is cooler. So, but as temperature as air flows across it, the air temperature also rises. So, the device temperature also rises owing to the boundary layer that grows on it. So, this, as you can see, is the situation. So, now what happens? The power level is kept same, but the heat source size is shrunk. So, this is what happens. I kept the same power level, but the heat source size is shrunk. So, as you can see now, a very big dome or the peak happens at the center of the device, as it's the same situation, same flow rate, everything, except that the heat flux now went up dramatically, and so the temperature rises from what was 92 ish to 100 degrees. So, 10 degree rise already happened just purely by shrinking the power sources. And the location of the heat source, if we keep the heat source same, but where we keep it makes a huge difference in terms of temperature as well. So, if we move the heat source over to this corner, again flowing air from here to here, you see that the temperature is even higher than the situation where the heat source is kept at the corner. And if you go even worse, if we move the heat source to the other corner, temperature even rises even more. And so, cooling these corner devices are much harder than cooling the device at the center. So, usually the hope is that the heat sources are located in such a way that airflow, when it happens, is in a position to pick up heat from one source, and there may be multiple sources. As you can see in the laptop example I showed before, there are multiple, the memory device, the solid state device, the optical devices, optical drive, and the processor, GPU, you name it, all these devices are dissipating. There is usually a hub. So, all these are dissipating heat. So, each heat source is going to heat up the airflow, and that airflow, hot air, will make contact with the next heat source it comes into. So, that is the nature, and so the heat spreading resistance becomes very important to deal, as the heat has to be spread over a larger area, then heat needs to be dissipated. Often pulling or putting a solution on these small devices may not be that helpful if you do not spread the heat. So, here is a question. So, we kept the power same, but what happens as we change the device sizes? The power level is same, what will happen to the average temperature of the heat source? If you see, the average temperature will remain the same, but only the maximum temperature will keep changing. So, the maximum temperature will be much higher for this case compared to this case, and this case, if the power level is same. So, the next question, how do you report heat flux? I have two heat sources now, or one heat source, and I have two areas. One is the source area and the other is the plate or the heat sink area, which has a certain thickness. Now it is spread over a larger area. So, if I were to design a heat sink, I will use the heat flux at this level, which is AP. So, we divide Q divided by AP. However, Q divided by AS is required for spreader design. So, depending on what you are looking for, so one has to specify the area which is used. So, you can't just report heat flux is 100 watts per centimeter square without telling which area, so that we are talking about. So, this is a common confusion that happens when just a heat flux is specified without telling what area is used, and also the temperature associated with that particular area is also required to be specified. Anyway, the last question, if I were to have a heat sink, and as you can see here, this is the resistance of a heat sink, and there is a base of the heat sink where the fins are now sticking out like this. Will there be an optimum thickness? Why should there? If there is, why should there be optimum? In such situations, here is an example. You can think of this as some fins sticking out, and that is the average resistance is what is drawn here. So, you can see that there are typically, if I were to draw the resistance versus thickness, at small thicknesses, if this is my thickness that I am interested, T, at small thicknesses the resistance will be, the spreading resistance will be very large. However, this resistance is Kelvin per watt, this is in millimeters or meter. So, the spreading resistance will be large when the resistance is, when the thickness is small, and it usually falls off to a certain, it may asymptote to a smaller and smaller value as you increase the thickness. On the other hand, the bulk resistance of the conduction, which is nothing but T divided by thermal conductivity of this material times area, this thickness, as you keep increasing, this resistance rises. So, it rises linearly. So, as you can see, there is a nice optimum thickness. This is the thickness, best thickness one can resort to if one were to balance. Otherwise, this will start to dominate and the resistance of this spreader base starts to increase because of the bulk resistance. And keeping it suboptimal will also result in larger spreading resistance. So, usually there is an optimum resistance to these devices, and that is what is discussed. What this means is that there is always, when you have a convective heat transfer coefficient or a heat sink mounted as shown here, airflow is happening, small heat source mounted on the bottom of the heat sink or epoxied or glued to this heat sink. What happens is that the total thermal resistance from the temperature here to the temperature here, T air or T inlet, this resistance T max minus T in divided by the power dissipated by this device. If I were to draw, the curve looks like this. Essentially, this is a very important curve. What we are plotting is a total thermal resistance as a function of convective heat transfer coefficient. Typically, natural convection is in this regime. Natural convection heat sinks or natural convection coefficients are on the order of 1 to 10 watts per meter square Kelvin. And if you turn on a fan, usually you are in the forced convection regime. And here we need to go for liquid water or liquid cooling. And beyond up to let us say 2000 or 3. Beyond this, it is two-phase cooling, where your boiling flows occur or some sort of phase change occurs. So, you can see that we have gone to higher cost solutions. We have moved from natural convection, where there is no need for fan, to a forced convection where a fan is needed that blows air across this heat sink, and even then the drop in the total resistance is not that high. And as you go to smaller and smaller, because sometimes we need to achieve very small resistances or small resistances because of the high power. So, your spreading may be the real reason here. In this case, it is actually the case is that the spreading resistance is the dominant regime, and any increase in heat transfer coefficient is not helping the total resistance, because the spreading resistance is the dominant factor. And typically it has the heat transfer coefficient has a logarithmic dependence, while the B is the other constant. A and B are constant here. So, your convective resistance goes by logarithmically, but your the spreading resistance is dominating in such situations. So, what we need to do is that ensure that the spreader is sized properly before mounting a heat sink. So, otherwise one can go to extremely high cost solutions, where here in the liquid cooling you need a pump, you need to circulate. Once the liquid picks up the heat, it has to still dissipate, to be dissipated to air. So, you have another device for cooling the water, that is, or liquid that is flowing and picking heat. So, you have two, one a radiator type device and one cold plate that picks up heat at the heat source. So, your cost is increasing. This is the heat transfer coefficient increasing, means cost of the solution, thermal solution, is increasing. So, one has to ensure that the spreading resistance is carefully designed, so that one can effectively use low cost thermal solutions. Otherwise, one may have to go to higher solutions, costly thermal solutions or heat sink solutions, if the spreader resistance is not properly, or spreader is not properly designed. So, the last part of this introduction piece is the contact resistance. So, any time we bring two materials together in contact, only 1 to 2% are in contact. If I put my two hands together, two arms together and palms together, I see that very little contact is expected if I put very light load, and this is true for any heat flow device. So, in this case we have a material 1 and a material 2, and heat is flowing from the top, and usually what happens is it tries to go through these, because these pockets are filled with air, or if it is in vacuum, it may be in vacuum, only radiation may happen. So, these spots are called solid spots or contact spots, and heat will flow only through these guys and spread out. It will constrict, heat flow will be constricted to go through these spots and then spread. This contact resistance of these solid spots are nothing but the constriction of heat flow from the top material to the bottom material, the contact spots, and this is spreading, and this is. So, some of the work that we discussed on spreading is equally important, but then the contact resistance and the spreading resistance for same area ratio change are same. So, there are many modes of heat transfer, that conduction, convection inside, conduction in the interstitial gap, and if the interstitial gap is filled with some material like thermal interface material, then one has to account for conduction in those materials and radiation and so on. So, usually these convection in these, because of the size of those contact, the gaps in those between the materials are small, that convection is negligible. However, the contact resistance has to be accounted for wherever there is bare metal to bare metal, or as we discussed, thermal interface material has to be used to mitigate the transfer of heat from the heat source all the way to the heat sink. And some of the design of these contact resistance or the thermal interface material are quite challenging. However, we will not talk about them as part of this course. So, we what we discussed so far is the introductory part, where we tried to highlight what are the issues in designing heat sinks or the convective heat transfer based cooling solutions for thermal management of power devices, the electronic devices. Here we are going to encounter the other question, which is what heat transfer coefficient that we should be using, because the situation you will see that quickly becomes fairly complex, and many of the analytical treatments are totally cannot be used directly, and one has to use judgment to make sure that we use the right set of materials. So, heat transfer coefficient, as we discussed in the last introductory material, there are forced convection, natural convection, typical mean heat transfer coefficients are average mean. Here is the average heat transfer coefficients are on the order of 1 to 10 watts per meter square Kelvin, and for forced convection it is about 10 to 200 or 100, 150, whatever you specify. Then forced convection with water, liquid metal, boiling, pool boiling, low watts per meter square Kelvin, and forced convective boiling, you have very high heat transfer coefficients, and condensing and so on. So, you see that depending on the need, one may have to choose. If we are talking about very high power fluxes, then one may have to resort to some kind of liquid flow or liquid cooled solutions or two phase solutions and so on. But this is at a level when we are talking about a single heat source or a heat source that is manageable. Let us look at a situation, a typical situation depicted here as schematically. In a electronics cooling from a system perspective, you see that is an example where there are 5 PCBs are mounted, and you are trying to cool them using a single fan array, and let us say these are some dummy components or heat dissipating components that are there. So, in this arrangement you have 5 inlet vents, 1, 2, 3, 4 and 5. So, these 5 inlets 1, 2, 3, 4 and 5, and air flows, picks up heat from here and leaves the system as exhaust. So, one can apply first law and do the analysis. However, the question arises, there are in here you can see that these orifices are, some are large, some are small. So, that is to say that some of the heat dissipated by the components here may be much higher in comparison to these guys. So, that is why larger airflow is required or demanded. So, airflow balancing is done, and it is done in such a way that the flow lengths are maintained same. This length is equal to this length. So, that there is no distribution issue, flow distribution issue from a single fan, and on top of it we have to ensure that some PCBs need more airflow compared to the other PCBs. So, those are also managed through these orifice sizes. Coming back to this, now you can see that the power levels are changing, the geometry is also changing everywhere. So, how do I define, typically when we approach a convective heat transfer problem that we discussed, is that we calculate a Reynolds number, go look for a correlation if we can't find an analytical solution, get its heat transfer coefficient. After finding the heat transfer coefficient, knowing the surface temperature, we calculate the amount of heat that can be dissipated by that arrangement. However, here there is no geometric similarity, or you have often need to encounter turbulent effects, entrance effects, and a heat transfer definition itself, or the Nusselt number, what characteristic length, if I were to take it at a heat sink level, flow going between the channels, then the heat transfer coefficient or the Nusselt number will be different. While I am talking about a PCB level, my heat transfer coefficient, what would I define? What is my hydraulic diameter? Will it be the height of this heat sink, or will it be the height of this, and so on. So, you are running into multiple levels or multiple questions than answers, and how heat is dissipated by the substrate and so on. So, you really need to focus on what scale to use and how one can solves approach this problem. So, you do not have geometric similarity, that is the primary problem in many of these devices. If you look at as I just discussed now, you are dealing with at the system scale, which is 100 centimeter scale, your Reynolds number will be on the order of 100,000. At the PCB level, it can be 10 centimeter scale, and the Reynolds number will be, if I were to use that as a hydraulic diameter. If it is at the chip scale, it is 1 centimeter. So, you are running into a variety of scales and variety of Reynolds number, and what is the heat transfer coefficient, or which is the right heat transfer coefficient, is the question that we typically address. And that is what we will talk here. And here is an example where there are 3 heat sources in a very simple, they are separated by equal distances, and these are not common in actual practice, but for the sake of discussion we are seeing that there is flow happening from left. There are 3 sources that are protruding from the green area, which is the package. Then there are 3 of those, then there is some radiation from the top wall and heat convection loss to the flowing medium. So, these are the situations that we encounter: conduction, convection and radiation. All 3 effects are encountered because heat will be conducted from the package to the board, and heat can be dissipated from the board itself to the incoming air. So, how do I work? What heat transfer coefficient should I use is the question that we always encounter, and let us look at some few other aspects in the design of heat sinks. We will discuss heat sink design in the upcoming modules. For now, we will just look at that there will be heat sinks without any air gap, or this is called a ducted heat sink arrangement. When there is a small air gap, which is common, is called the tip clearance, or the top plate can be called a shroud. And if there are airflow in telecom circuits, this is common, is that there are airflow through the sides and on the top. These are called side bypass with tip clearance, and you can have transitional flows, recirculation regions, swirl flows, because there is a fan, it will induce a certain swirling motion and elevated free stream turbulence and so on. So, one has to account for all these characteristics when discussing heat transfer problems. As we discussed, this is just the change, the changing, the heat sink size will change, the spacing between the components will change. So, geometry is going to keep changing everywhere within the circuitry or a PCB. So, there is no generalized relationship for these situations. One has to make strong judgments, and we will discuss what it is. For example, this is the example we discussed in the previous module. This is your processor area, and these are vents where air is pulled in by this fan, and the air pulled in will cool little bit of this, but then it gets this heat from the processor through this copper heat pipe is delivered to a set of fins. These are the fins that are the heat sink, and air is blown across this, and this vent is the exhaust vent that if you put your hand usually you will see, and this vent is again used to cool the solid state devices, the memory and so on. So, now you can see that there is no geometric similarity, there is no uniformity in where the heat sources are placed and so on. So, one has to work on, this is another example, and this is an example of a workstations. You can see that these are places where memory devices are mounted. So, you will see enormous number of components that need to be cooled, and that is the challenge encountered in electronics cooling circuitry. So, we will look at as a simplest form, we will try to make use of the integral method that we developed in the past in the last as part of this course, and start with this unheated starting length problem. And this is a very powerful problem that can eventually give a very important concept for adiabatic heat transfer coefficient. So, we will discuss that in the next module as we move forward.